Kyle, I know you, I see the hand, you know, but go ahead.
In the Z direction for, the depth can vary based on number of boxes, but are each of those lengths the same? They're all below the surface?
They are, and that's an artifact of CH3D. It doesn't have to be.
Okay.
You know, you could have, when we read them in the first time, we could have read them in as varying. That's just an artifact of CH3D. If volume is not conserved, the model will blow up. All right, so here's, you know, you've got these boxes, and this actually is by intention. I won't call it my intention, but I'll say it's by intention. What ICM does is it computes these volumes based on the flows in and out. So at every time step, it takes the flows that come in and it recomputes the volume. Now, what ought to happen is this should not vary, so you shouldn't have any problems. The reason I say that this is, I'm going to claim that the people who did this coding did that intentionally, is, you know, you have to perform this procedure when you set the model up called linkage. Linkage is a nightmare. Well, I backstep a couple of steps. The way ICM works is the hydrodynamics are computed externally, they're saved, and they're read into the water quality model. So a different option is you run the water quality model simultaneously with the hydrodynamic model. I think EFDC does that. All right, so that's not how we do it. Going back a long time ago, we were really concerned with computer time. And you can get really hung up if you have to rerun the hydrodynamics every time you make a water quality run. Again, I think EFDC really has that problem. Or I can't say what it is today. I can say that years ago, it had that problem. So this, in a way, does away with that problem because you only run the hydrodynamic model once. I am personally on like around 250 water quality model runs for this phase of Chesapeake Bay, but we've only run the hydrodynamic model once, so wonderful. On the other hand, what's the disadvantage? You have to go through this process we call linkage, which is to take the hydrodynamic model grid, all of this, and somehow convert it to the water quality model formats. So for example, and this is part of the nightmare, CH3D is a structured grid. It works on IJK. So what somebody who was really a much better computer programmer than I did, he had to design software that would take the IJK specifications from CH3D and output the information we need to run ICM on an unstructured grid. And then, you know, you have to take the flows that are in CH3D as IJK and output them according to the face numbers in ICM. So, you know, the process is automated, but you understand you can screw up, right? How do you know you screwed up? The model blows up. All right, so if your map file isn't right or if something isn't right, what's going to happen to the cell is the flows that go in and out of it are not going to sum to zero, and eventually it's going to run out of volume and it's going to blow up. Or somewhere your model's going to blow up. So this is a very crude method of smacking you in the head and saying your linkage isn't right. Okay? So if you go through this linkage process, which I won't go into today, but those of you who want to do it, contact me later. I'll see what I can do for you. But intentionally, you know, if you don't have the linkage right, the thing is going to blow up. So if you do this and it blows up, go right back and say there's a problem somewhere, you know.
What's the tolerance on the volumes? There's got to be mass balance tolerance.
Yeah, and you know, I don't know exactly.
Related to the volume of the box itself, to say even if you have like 0.001 CMS difference, one day you multiply 86400, it will take a lot of like volume away.
Yeah, you may recover. I mean, we have the same issues with volume conservation. And it's not so much a linkage, it can be that the hydrodynamic model has some time stepping issues as well. And that they're trying to, reduce the runtime, so you may get some instabilities which result in a non-conservation of volume. And that just carries over the water quality model, and the model may edge through it, but you get some unusual results, or it blows up and you go back to the hydrodynamic group and say you got to rerun it. So the other thing, it's not necessarily always the linkage, it may be part, but it could also point to a problem with the hydrodynamic model on occasion.
You want a dirty little secret?
Yeah, dirty little secrets.
EFDC did not conserve volume. We've run this with EFDC. And we did the exact same process, which is we exported the hydrodynamics. And what we had to do was, actually I didn't do, but what had to be done was there's a way to specify evaporation.
Yeah.
And you know what I mean? If it doesn't work out correctly, we call that evaporation. And over time,
It works.
it works, but you can get some funky little results. So I'll talk only about EFDC and say if you don't have the linkage right, it blows up. But if it blows up, you got a problem, whatever model you're linking to, and you're going to have to either examine your linkage and say, I didn't do something right, or examine the conservation of volume from the hydrodynamic model and say it's not conserving, something along those lines.
What about all these rainfalls? Like, how do they treat rainfall inputs?
We have, I've got to say two things. We have something we call prevap, precipitation evaporation, and that can be specified. We don't use it in the Bay model, and frankly, I haven't looked at it in a long time, and I can't talk about it today. But you can precipitate, evaporate.
Okay.
If you work in Florida Bay, you need evaporation, and we did deal with that when we worked in Florida Bay, but I just don't recall.
Okay. So it's not part of this part, like time.
No.
Well, it would be part of it if the hydrodynamic model included it.
But
Because
still,
the volume, surface volumes would be changing.
but in the hydrodynamics model, it tracks all the inputs, right?
Yes.
I don't know, when I worked with WASP, in WASP, you still need to specify the external.
Well, yeah, but WASP is because it's not using the hydrodynamic model.
Yeah, we run the hydrodynamic model.
Oh, you're with
Yeah.
EFDC WASP, sorry, okay.
Yeah, but anyway, yeah.
On that line, can the literal flows be negative?
We've never done it. I guess it could be, but I don't think we've ever done it. Is there anything else I want to cover? Well, okay. Well, a couple other, why not, we'll go into it now. If you look at the diffusion there, you see what you're reading in it is diff from the number of horizontal flow faces plus 1 to the number of flow faces. So what you're reading in actually is the vertical diffusion, which varies in time. The horizontal diffusion or diffusion in this direction is read once. It's the same for all flow faces, and that's all there is to it. In the Chesapeake Bay version. Why is that? Number one, it tends to be negligible. Number two, when we invented this model 30 years ago, dispersion was a dirty word. It had 4 letters, and right, you see the smile on this guy's face. But it was a dirty word, and people who were on our review panel were famous for not liking dispersion. So seriously speaking, it tends to be, in Chesapeake Bay, in the longitudinal and lateral direction fairly small when you're running a hydrodynamic model with time steps of a minute or two, okay? The rate of dispersion got a dirty name was when you used to average hydrodynamics over longer periods, like 12 hours. You had to, the mixing that took place by averaging out the tide was treated as dispersion. So since it was negligible, and since people we were dealing with didn't like it anyway, and since, go back 30 years ago, computer storage was a big issue for us, okay? You know, run this model for a couple of years, store all this information, read it back. In those days, you really had to worry, okay? So for a number of reasons, we read in one horizontal dispersion value or diffusion value, and it's constant. There you are. This has caused me no matter of headaches, a little bit in Chesapeake Bay and certainly elsewhere, but I'm just going to tell you, for the moment, for the Chesapeake Bay model, that's the way it is, okay? If you apply it elsewhere, you can deal with it there, but, you know, for the moment, that's the way it is. A couple of places where I wish I could use a little either real diffusion or artificial dispersion, particularly in getting the flows, mixing in and out of small tributaries. In the upper bay, I don't know what, some of those rivers over on the western shore, I really wish I could put a little more salt in there. And, you know, whatever the process is, I don't know, but if I were tuning the model, I'd turn up the dispersion a little bit. But since I can't do that, we make do. But, you know, you should just be aware that this is the situation if you're going to run the Bay model. And if you're going to apply it elsewhere, you're going to want to take a look at the code and, you know, get some time variable dispersion in there. Let's see, anything else?
Time varying or space varying?
Oh, excuse me?
Time varying or space varying?
For the longitude and lateral, it varies neither in time nor space.
No. But you would like to have?
I'd like to have some spatially varying dispersion in there. And I think there's some things going on with, you know, maybe circulation at the mouth of these small tributaries, wind mixing. You know, there actually is random processes out there that mix things, you know, despite what my mentors told me. And I'd like to have that in there, but, you know, we're rehashing old news. Let me see, any other questions?
So in your real application, you know, you have two numerical methods, like one is upwind, one is the quickest, to simulate, to calculate the advection. But if you use quickest, you reduce the numerical diffusions, then you add some of the dispersions to it, or how do you, I guess it's a real application question, like if you use upwind, you pretty much don't need any dispersion here because you have numerical ones. But if you use quickest, which reduces numerical diffusions, but then you specify some.
That's correct.
Dispersion coefficient.
Yeah.
Oh, okay.
Yeah. I think we're going to wrap this lecture up, and some of us are going to get coffee, and some of us are going to move our cars for the next 15 minutes, right? Or both. I hope let me. There's one more thing I ought to cover. Then we'll let you do it. Let me just go down a little bit. Okay. When you do these numerical integrations of differential equations, what you have to specify is the time step. You know, when you advance in time from one time step to another, what should the time step be? And I won't go into details, but the time step just can't be infinitely large, you know what I mean? Two things happen. One is you lose accuracy, and secondly, eventually, if it's too big, it blows up. So, you have two options with ICM. One is you can specify a constant time step. And the way you arrive at that time step is either you do some external estimates of what the time step should be, or you just hack it. Let's try, you know it shouldn't be too long, right? So you just hack the time step. But you can specify a constant time step. The other way is what we call auto-stepping. And this was something that was designed by Tom Cole. What he does is, internal in the model code, he computes the maximum time step you can take. And that varies. Because, if the flows vary, for example, the maximum time step depends on diffusion and on velocity. So if the flows are changing, when things are moving quickly, you need a short time step. When things are moving slowly, you can take a long time step. So what this algorithm that Tom devised does is it goes through the entire grid, all the faces. It finds the face that's holding things up, if you will. It finds a critical time step. So you will specify, if you use this option called auto-stepping, you are asked to put something in, let's say the value 0.9, you will always be taking a time step that is 90% of the maximum allowable time step. So this optimizes your run, if you will, because you're always pushing. If you specify a constant time step and you hold it through the whole run, there may be times where you have way underestimated what your maximum time step could be. So for the most part, although not always, for the most part, we use this auto-stepping. And that's in the Bay program, we use the auto-stepping. So you'll see that in your, and is there anything else I want to go over? Boundary conditions. Okay, well, it's 10, so we're going to take, we're at 10:05. Let's take that 15-minute break, and we'll pick up when we come back, okay?